Hello, my name is Andrew Ferrier. I'm a principal software engineer within the Xbox Advanced Technology Group, focusing on CPU, systems work, and general multi-threading, especially around game engines. So, running your server in the cloud actually has some special considerations that you need to take into account. In many cases, you're sharing that hardware with other customers because the cloud provider is going to basically buy more powerful machines than your specific instance that you're using. And this sharing is managed by an underlying hypervisor. And obviously within Azure, which is Microsoft's technology, we're using Microsoft's hypervisor, which is called Hyper-V. And today we're going to cover some of those issues that show up and also how to actually mitigate and detect when they're happening. So let's start with a couple definitions. There are three different types of cores you need to take into account, or CPU cores. The first is a physical core. This is an actual core that's on your die. For example, your desktop i5 may have 4 actual physical cores. The second is a logical core. These are effectively, when you're on a hyper-threaded machine, these are where you've got 2 shared logical cores on 1 physical core. So like, for instance, Intel calls this hyper-threaded. And you can actually call within Windows, get logical processor information. This will give you all the details on your physical and logical cores on your machines, cache layouts and such. So on a lot of processors, there's a one-to-one mapping between physical and logical, so throughout this talk, I'm just kind of use them interchangeably. However, there's this third type of core, and this is called a virtual core. And this is what's actually the term we use when you're running on a hypervisor. And what's happening is, depending on the performance that you need or you're using within your particular instance, you may not get the total physical core. You're actually going to get a smaller piece of a virtual core. And if depending on how much you need and how powerful that physical core is, you actually may be sharing that physical core with other customers. If you actually call get logical processor information on your server that's running in the cloud, you're actually going to get the simulated cores that the hypervisor is telling you that you have. So, what is a hypervisor? It's an underlying piece of software and/or hardware that allows you to run multiple virtual machines on a single physical machine. The idea being is reduction of hardware costs and provide extra security as well. So each virtual machine is totally unique and there's no direct communication allowed between them. So how the hypervisor works is actually very closely related to just how your general thread scheduler is working. Each virtual core is going to be given time to run on the physical core. And if you'll just run into this on basically any cloud provider, because they're going to run a hypervisor underneath. So since the hypervisor is mapping these physical cores to virtual cores, there actually doesn't need to be a one-to-one mapping. For instance, you may get virtual core 2 and 3 within your machine, may actually be mapping to physical core 17 on a particular hardware blade. So in Azure, each of those blades is running, of course, Microsoft's technology, Hyper-V, and you're running several virtual machines on that blade. Allocating time is needed between them, and again, this is all based on whatever instance type you've chosen to use. So the hypervisor is managing this virtual core time with something called time slicing. Time slicing works the same way a thread quantum does within Windows, which is how much time each thread gets before the scheduler automatically switches you out and gives time to somewhere else. However, the hypervisor tends to be at a very particular heartbeat. On Azure, and within Hyper-V, this is actually set to 10 milliseconds. And so what this means is, every 10 milliseconds, the hypervisor is going to switch to another virtual core, to maybe even on another operating system. However, depending on what instance type you're using and what generation of hardware you're using, you may not get that full 10 milliseconds. On newer generations of hardware, you can actually do more work, and basically you can do the same amount of work in less time, so you're going to get less of that 10 milliseconds. And so you can actually get to the point where you only need 4 milliseconds of that time slice, and in that particular case, the hypervisor can actually map 2 virtual cores to 1 logical core, give each one 4 milliseconds of that 10 millisecond slice, and just not do anything for the other 2. So, and one key point to keep in mind here, though, is this time slicing is based on the physical core. and they're not going to be in sync between each of the cores. So this picture here was clearly showing what's happening. Here we've got two virtual cores. I'm going to just call them red and blue, or A and B, and they're running on one physical core. And you can clearly see that they're not running in sync. And these could be even two of your cores on your virtual machine. So here first A gets to run, then B gets some time to run, back to A, and so on. And you can see that little gray area. There's a little bit of time that's not actually being given to either core. You can actually see this happening if you're using event tracing for Windows along with WPA. This particular trace was taken with XPerf, and I'm just using sampled collection of data. So basically every X amount of time a sample is being taken to see what thread or what call stack is running. In this case, I have two virtual cores. I'm using an instance on Azure that only gives me two virtual cores. If you focus on just the highlighted sections, what you can clearly see is when the virtual core is not running. Those areas where you get back down to 0%, the virtual core is not given any time to run, so obviously you can't collect any samples. And you can also see where the high spot is, or that 100%. And if you look at the highlighted spaces, they're actually about exactly 10 milliseconds apart. However, you can also clearly see here that those two highlighted spaces are not in sync, which is showing you that the physical cores, your virtual cores, are not running in sync between each other. And also to take into account, even though you're losing part of the time slice, your wall clock time continues to advance when you're not actually running on that particular instance. So the time slicing the virtual cores lies at the heart of special considerations you need to take into account for your title. Due to the 10 millisecond time slice, it's actually hard to achieve a steady high frame rate. It's actually impossible to achieve a steady frame rate above 100 milliseconds, or 100 frames per second, because there's bubbles in time where the core is lost, sometimes in the middle of some frames and not in the middle of other frames. Let's say you're actually able to get your server running at 200 frames per second, which is, a lot of cases, is actually possible. So this gives you 5 milliseconds a frame. However, your title is only given 7 milliseconds of time for that 10 milliseconds time slice. So you can get a 3 millisecond bubble that's going to happen every other one of your frames. So you're actually going to see your frame rate jump between 200 and 125 frames per second. You actually might not think this is an issue, because who's going to run their servers that fast? I was actually worked with a couple titles that have done that, and they've basically, their server, because they weren't doing much within it, especially with no rendering, they could easily achieve over 100 frames per second. Luckily, it was a pretty easy issue to solve. All they did was run their server slower. So actually targeting exactly 100 frames per second actually aligns nicely with this time slice, because all the bubbles will happen between each one of your frames. So even though you're getting less time per time slice on newer generations of hardware, you still can do the same amount of work. So you're not going to have any issues there. You should still see your steady 100 frames per second. And also, it doesn't tend to be a problem at your lower frame rates when you go down to the 30 or 60, because the bubbles end up consistently in the middle of your frames, which helps to keep the overall frame time consistent. This also doesn't tend to be a problem if you're running a collector-distributor system. Basically, it's where all your server's doing is collecting all your network messages and then distributing them out to all of your clients. Because these don't typically run at a fixed frame rate. However, you should consider the amount of time for a bubble as an additional cost within your latency. So if you happen to get bubbles of about, say, 4 milliseconds every 10, every once in a while you're going to add an extra 4 milliseconds of latency. So the next issue is around locking your threads to individual cores. This is actually, a lot of titles like to do this, keep their cache usage under control, especially code that's written on a console where they know exactly what they're running. However, since the virtual cores aren't running in sync with each other, you can actually have issues with these locks that are shared between cores or between threads on each core. If a lock is held by a virtual core that isn't running when threads on the other core need that lock, they're going to be installed for their entire bubble. So let's take this case. The purple thread is acquired and happens to hold a lock, and when its virtual core is suspended. During this time, the blue thread starts up, and it's trying to acquire the lock, but it actually blocks. So the blue virtual core eventually loses time, at the end of its time slice. So it's lost here actually a decent percentage of its time slice based on when it wanted to acquire the lock. So, but eventually purple starts running again and releases the lock. However, the way the Windows thread scheduler works, since it knows about this lock, it immediately transfers ownership back over to the blue thread, even though that core is technically not running, because the lock transference is happening on the thread that is releasing the lock. So at this point, the blue thread and the blue core actually owns the lock. Purple attempts to reacquire it, but it can't because now blue owns it, even though it hasn't executed yet. So purple now ends up waiting for almost its entire time slice before it can acquire the lock again. So in this case, you may have a simple lock that maybe only takes you, say, a couple microseconds that you're going to hold, but now it's costing you several milliseconds of time. So in this case, on Azure, this would mean each thread is waiting on an average of 10 milliseconds to acquire that lock. So you may think this is actually extremely rare to happen because you're not holding your locks for that long. Basically, hopefully, definitely not in the millisecond range. The problem is, once it does happen, it'll cascade throughout your frames. Since that lock transference is happening immediately on releasing the lock back to a core that doesn't hold it. So as long as it happens once, from then on, your locks start hitting into the multi-millisecond range, which tends to push these later locks in. Here you can see in the second case, the purple wants to reacquire it, but it can't because the transference has already happened over to blue. I've actually personally seen this on a couple titles, and we'll cover in a couple minutes how to keep this from happening in your threads. So a lot of studios like to use spin locks to reduce the overhead time because it's expensive to go back to the kernel and back for the kernel locks. Basically, a thread just spins there waiting for an event to happen and then continue running, for example, waiting for a job to be added to a job queue. However, there are issues with spin locks, and you can actually get to a situation where you will deadlock your entire server, or at least one thread. The problem is the operating system doesn't actually know about the spin lock, so it can't transfer ownership immediately. Here, purple has acquired the lock and owns it when it happens to lose the core. However, blue now wants to acquire the lock. So it's going to spin during its entire time slice, effectively, or when it wants to acquire this lock, doing no work, just sitting there spinning. When purple finally runs again, it actually, since the OS doesn't know about the spin lock, it can't transfer ownership immediately over to blue. So what then happens is purple runs again, reacquires the lock, and then loses its virtual core. So now blue has to wait an entire time slice to reacquire that lock because it can't acquire it because the OS doesn't know anything about it to transfer the ownership. So in this case, a spin lock was used to save, in the long run, a couple microseconds of time going to the kernel and back. However, it ended up costing over 10 milliseconds of lost time. It gets even worse because this entire time B is sit there spinning, doing effectively no work. No other threads can actually get time to run. So you may think this is a rare case, but it's actually been seen in the wild. However, the nice thing is you don't tend to get the cascade effect because the lock is not being transferred immediately. And so you actually have to hit multiple cases where you're holding the lock over a time slice, and that's a lot rarer. So how do you work around these issues? So in the end, there's only one absolute rule to improve any multi-threaded performance, and that is reduce contention. So every piece of communication between your threads adds some point of contention between them, which is going to slow down or cause possible issues from this time slicing. The communication is either through effectively locks, signaling, or any type of waiting. For example, there's some studios have rules about using semaphores versus using busy waits. However, there are cases when the busy waits are more performant than semaphores, but there are actually an equal number of cases where semaphores, actual kernel semaphores, are more efficient than those busy waits. It all depends on the number of threads that you're running, what cores they can run on, and any contention that's happening between your threads. In this particular instance, on what version of Azure or what instance you're using within Azure. So the best solution is actually neither, which will give you zero contention. So there's several strategies or algorithms that help reduce contention between the threads. The first is what's called lock-free. So lock-free doesn't actually mean totally without locks. What it means is there's no possibility of a deadlock within the system. As long at least one thread is always continuing and making progress on its work, it can be considered lock-free. For instance, you'll see a lot of lock-free code tend to use small compare and exchange, just keep comparing and exchanging a value, interlock, compare and exchange until it's successful. That's an example of, basically it's a lock-free system, however threads can sit there just spinning forever, but at least one thread will always be making progress. The second is what's called wait-free. And these tend to be a bit more complicated. In a wait-free algorithm, the definition is every single thread has to always be able to make progress. You're not even allowed to have any little spin locks with these, like for instance, the interlock, compare, and exchange, because there can be no potential of a stall on any thread ever. For instance, if your data structure is using job queues that a lot of threads can access, try and convert over to a wait-free algorithm, because this will guarantee all your threads can continue running and continue accessing the data. And this will remove any potential issues you have on your threads on stalled virtual cores. So the last is work stealing. This is an efficient method to automatically balance your work between your cores. It works very well even with jobs that cost different amounts. The general idea is that each thread is only going to, when it stalls, is going to pick up work from other threads. And the way it's doing this is every single thread has its own job queue. And the only time a thread is even talking to the job queue of another one is if it needs to steal work. But in that case, it's actually okay if the stealing thread stalls, because by definition, it has no other work to do anyway. The nice part about work stealing is, since each thread has its own job queue, you get almost no cache contention between your threads. I've used this in a couple job systems to almost achieve perfect scaling across the number of cores. So picking the right algorithm based on your needs can actually have a pretty drastic performance effect. It's all based on your average job count, your job size, the contention for whether one algorithm will work for you or the other. So basically try it out, different algorithms out, if you can swap them out based on your particular usage within your title. This allows you to profile each one and pick the one you want. So going back to this time slicing, it's actually possible to detect at runtime when this is happening. The trick is you sit there and start up a thread that's high priority and sit there in a really tight loop calling query performance counter and watching the clock. Because the true wall clock time will jump across the bubble. So just look, as your time will sit there steadily increasing with its query performance counter, you suddenly will hit a jump. Right when that jump happens, you're at the beginning of your time slice. And that's actually a good time maybe to start your frame. If you can actually easily achieve the 100 frames per second, start your frame right when that clock jumps. You don't want to do this. The time slice actually it will drift a little bit, but not that much. So you don't want to do this that often because you're spinning this really high priority thread. We usually recommend you only have to resync about once every couple minutes and you'll be fine. However, one thing to consider is the cache will be cold at the beginning of your time slice because there's no guarantee on what was running when you lost that bubble. So depending on whatever instance type you're using and the overhead of your core, it can actually be useful. I've seen a lot of titles switch to a single threaded model. A lot of engines will do this. This totally removes all your contention that you're going to have. You don't need to worry about any stalls from any of your lock spins held between the threads when you're actually going to lose that core. It also allows better scaling. You can start doing cost-benefit analysis. So if your server can run on a single threaded, it may be better for you for a cost analysis to actually use more powerful instances within Azure and run multiple servers within one instance. It all depends on your particular title, so you should basically just send out a spreadsheet, figure how many servers you can run on one particular instance and how much you're paying per hour of that instance. You can easily find out what's best for you. Another situation is to allow your threads to float. This tends to be more common within the Windows system because you're running with a lot of other stuff. Console titles don't do this. They tend to lock their threads. However, if you allow them to float between the cores, you're going to get a naturally balance and they'll be swapped back because idle cores will pull threads to them. So more importantly though, if a thread holds a lock, when it loses the virtual core due to the time slice, if another core goes idle, it can pull that thread over to it, which will then cause it to release the lock faster. So going back to that previous case where we had the thread actually acquired the lock, it released it, and another thread wanted it, and so the lock was ownership was immediately transferred to the virtual core that was stalled. In that particular case, that thread then goes idle, and that core goes idle, so it'll now pull the thread over to it that was running and holding the lock, which will release it a lot faster. Definitely avoid busy waits. You're just spinning and wasting resources that can be given to other threads that need time to run. Since the core doesn't go idle, the scheduler will not pull threads over to it within Windows. It doesn't matter if there's a ready high priority thread on another core. The Windows scheduler is very resistant to moving threads between cores. This really helps a lot with cache efficiency, for instance. And so it's only going to pull a thread over to it if it goes idle. If you're spinning, just doing busy waits, you're never going idle, so this is going to happen. So usually also recommend, though, if you are doing any type of spin loops or any type of busy waits, make sure to add telemetry around them so you know how much time you're actually losing to them. And that's it. Questions?